Okay, students, let's start with the past papers for specific heat capacity related to O levels and IGCSE physics. Let's move on to the first question. A hot steel rod is cooled by plunging it into cold water as shown in figure 3.1. Okay. The steel rod has a mass of 2 kg and is initially at a temperature of 500 degrees centigrade. Okay. It cools to 50 degrees centigrade when placed in water. Okay. The specific heat capacity of steel is this. You are basically given the mass, you are basically given the initial temperature, final temperature, and the specific heat capacity, that is a small c. You have to calculate the thermal energy lost by the steel rod as it cools to 50 degrees centigrade. How can you do that? Q is equals to mc delta T. Now, what is your mass? Your mass is 2 kg. What is your specific heat capacity? 460. You have to make sure the mass is in the same units as the specific heat capacity. Multiplied by change in temperature, that is 500 minus 50 is equals to what? Let's calculate that. 500 minus 50 into 460 into 2. This comes out to be 4.14 into 10 raised to the power of 5 joules. Simple as that, nothing complicated. Let's move on to the next question. A small mass of water, okay, boils when the rod is placed in the water. The remaining water then cools to room temperature and some of it evaporates, okay. A small mass of water boils when the rod is placed in the water and the remaining then cools to room temperature and some of it evaporates, okay. In both boiling and evaporation, water molecules escape into the air. Okay. State one way in which boiling is different from evaporation. Very easy. Boiling occurs boiling occurs at a single temperature known as boiling point. Single temperature known as boiling point. However, evaporation can occur at all temperature. However, evaporation occurs at all temperatures. Let's move on to the next part. The rate of evaporation decreases as the water cools. Explain why this happens using ideas about molecules. So, as water cools, what happens? Temperature decreases, and as your temperature decreases, average kinetic energy of molecules decreases. Average kinetic energy of molecules decreases. And as average kinetic energy of molecules decreases, what will happen? There are there are fewer there are fewer particles or molecules left with left with the energy to escape from the surface. Left with the energy to escape from the surface. Simple as that, nothing complicated. Let's move on to the next question. One type of renewable energy source is shown in figure 4.1. Okay. This is the hot steam up, this is the earth surface, this is the cold steam down. Okay. State the name of the type of renewable energy source shown in figure 4.1. This is geothermal energy. Geothermal energy. Okay. Let's further move ahead. 100 kg of cold water at a temperature of 20 degrees centigrade is pumped down to the hot rocks. Okay, 100 kg of water. The water returns partially as steam and partially as hot water. The steam and the hot water are both at the temperature of 100 degrees centigrade. The specific heat capacity is this. This is your final temperature. This is your initial temperature. This is your mass. Okay. Calculate the energy needed to heat 1000 kg of water from this to this. So Q is equals to mc delta T. Your mass is 1000 kg. Your specific heat capacity is 4200. And your change in temperature is what? 100 minus 20. What will your heat come out to be? Let's calculate. 1000 into 4200 into 80. This comes out to be 3.36 into 10 raised to the power of 8 joules. Let's move on to the next one. Explain why more energy is transferred when 1 kg of steam cools to 20 degrees centigrade than when 1 kg of hot water cools to 20 degrees centigrade. You should include a reference to the arrangement of particles in liquid and in gases in your answer. Okay, very easy. Okay, so to answer this question, first of all, you need to see the examiner is talking about two things. In the first thing or in the first pathway, you have 1 kg of steam, that is a gas, and you have to convert it to 20 degrees centigrade of liquid. Okay. In the second scenario or the second thing, you have to convert 1 kg of water that is already liquid into 20 degrees centigrade of water that is also liquid. Can you see when you are considering steam, there is a state change happening. So you can write here if steam is to be cooled is to be cooled to 20 degrees centigrade, then if steam is to be cooled to 20 degrees centigrade, then gas condenses to liquid. This results in bond formation and hence more energy more energy is required for cooling is required for cooling. Simple as that. Let's further move ahead to the next question. Figure 4.1 shows the atoms at one instant in a sample of iron at a temperature below its melting point. Okay. State the lowest possible temperature on the Celsius scale and on the Kelvin scale. The lowest possible temperature is 0 Kelvin, and on the Celsius scale, this becomes what? Negative 273 degrees centigrade. The temperature of the solid increases, the sample still remains a solid. Describe how the motion of the particle changes. The particles start to vibrate, start to vibrate with a greater amplitude, or you can say with a greater kinetic energy. The particles start to vibrate with a greater kinetic energy. Now, why have I said that? See, basically, the temperature is increasing here. Nothing else is happening. If your temperature increases, that means your kinetic energy will increase. You will say the particles start to move with a higher kinetic energy. Also, since this question is of 2 marks, you can also write one more thing. The particles move with a greater amplitude. You can add this just for safety with a greater amplitude. With a greater amplitude means that particles start to displace more now. The solid melts. State what happens to the internal energy and temperature of the solid as it melts. Internal energy increases. What happens to the temperature? It remains same. Let's further move ahead. A student places a 300-gram piece of iron in boiling water until the iron is at a temperature of 100 degrees centigrade. Okay. So the initial temperature of iron is 100 degrees centigrade. You have the mass as well. He removes the iron from the water, okay, and places it immediately into 100 grams of water at 25 degrees centigrade, okay. This is the mass of water, this is the initial temperature of water. The iron cools and the water warms until both reach this final temperature. The final temperature of both of them is given to you. The specific heat capacity, small c, of water is also given to you. No energy lost is to the surrounding, okay. Calculate the change in energy of the water as it warms up. So Q is equals to mc delta T. Your mass is what? For water, 100 grams. What is the specific heat capacity of water? 4.2. What is the change in temperature of water? Initially it was 25, then it became 44. So 44 minus 25, this becomes what? 44 minus 25 multiplied by 4.2 multiplied by 100. This comes out to be 7980 joules as your answer. Calculate the specific heat capacity of iron. You have to calculate the specific heat capacity of iron. So first of all, what will you say? The energy gained by water is equals to what? Energy lost by iron. Energy lost by iron. Okay. So what was the energy gained by water? 7980. What was your mass of iron? 300 grams. Okay. What was your specific heat capacity of iron? You don't know. What was your change in temperature of iron? 100 minus 44. So 7980 divided by 300 into 100 minus 44. This gives you a value of 0.475 joules per gram degree centigrade is your specific heat capacity. Simple as that. Let's move on to the next question. Okay, let's see this question. Figure 9.1 shows the structure of a water cooler that is used to supply cold water to the workers in a hot office. Okay. The reservoir of water. Okay, so the reservoir of water is this. Okay. In the plastic container is at room temperature. Okay. It does not mix with the cold water in the tank below. Explain why. Why does water at room temperature does not mix with the cold water in the tank below? Let me show you what the examiner is talking about. This is your, let me highlight it, it will be better. This is your water at room temperature. This entire thing is your water at room temperature, and this thing is your cold water. Why is the hot water or water at room temperature not mixing with the water at with the cold water? Yes. Any ideas? It is really easy. Any ideas? The water at room temperature does not mix with the cold water. Why? Because cold water sinks to the ground. You can write here. Because cold water is more dense, is more dense and sinks to the ground. Sinks to the bottom will be better. Sinks to the bottom and doesn't mix with the water at room temperature. At room temperature. Simple as that. Also, you can write the water at room temperature floats above the cold water. Above the cold water. Simple as that. In examination, make sure you adjust your writing according to the line spacing. When the tap is opened, water at room temperature from the reservoir flows down into the tank. Cold water from the tank flows out from the plastic pipes and out of the tap. What is happening? If you open this tap, this thing flows downwards, and this cold water goes through these plastic pipes and out of the tap like this. Okay, that makes sense. Okay. Cold liquid from the refrigeration unit is pumped through the copper pipe and thermal energy passes through the copper to this liquid. Okay. Suggest why the pipe is made from copper. Copper is a good conductor of heat. Copper is a good thermal conductor. Is a good conductor of heat. Let's not be fancy here. Is a good conductor of heat. Let's move on to part 2. Explain in terms of free electrons how thermal energy is transferred through the copper. Okay, so copper is a metal. How will thermal energy be transferred in a metal? It's very, very easy. Electrons are moving, or you can say free electrons are moving. Free electrons are moving across copper, across the copper metal, or you can say copper. These electrons, these electrons hit or collide with the molecules, with the molecules and transfer energy to them. Energy to them. Simple as that. This process will keep on going until you reach the other end of the metal. As the water near the copper pipe cools, it begins to mix with the rest of the water in the tank. Explain how this happens. Okay. So, as the water here cools, what will happen? It will become, it will contract. Basically, its volume will shrink. It will become more dense because we know density is inversely proportional to volume. As you cool something, its volume decreases, its density increase. This cool volume or cool water will flow down, and hot water, or you can say warmer water from the bottom, will come to the top, and that will get cooled consequently. This is basics of a convection current. Okay. So how will we write it? Let's write it. You will say as the water near the copper wire cools, as the water cools, it contracts, or you can say volume decreases. Consequently, density increases. Density increases. And as density increases, what will happen? Consequently, density increases. As density increases, as density increases, what will happen? The water near the copper wire, copper wire, copper wire sinks to the copper pipe, I would say. Here we have written copper pipe, so we will refer it as copper pipe. Copper pipe sinks to the ground. And last point, if cold water is sinking to the ground, what will happen? Less dense or warmer water will rise up. Less dense, warmer water rises up, rises up and takes the place of cold water, takes the place of cold water. Simple as that. Let's further move ahead. The tap is open and water flows at 21 degrees centigrade from the reservoir into the tank. Okay. The specific heat capacity of water is this. This is your initial temperature. Calculate the thermal energy removed from this mass of water to reduce its temperature to 7 degrees centigrade. Q is equals to mc delta T. What is your mass? 250 grams. Now, can you see this is in grams, this is in kg? So, you will have to convert the mass into kgs. 0.25 into specific heat capacity, that is 4200. What is change in temperature? 21 minus 7, that is 14. What does your answer come out to be? 0.25 into 4200 into 14. This gives you an answer of 14700 joules. Simple as that. Describe the motion of the molecules in a liquid when there is a uniform temperature throughout. Now, how do molecules in a liquid move? They move in clusters and slide over each other. I guess I've written both the key points here with the same statement. The molecules in liquid move in cluster and slide over each other. Each other. What are the two key points here? They move in clusters. They move in clusters and they slide over each other. These are the two key points that you need to remember. State what happens to the motion of molecules in a liquid as the temperature of the liquid decreases. Their speed or kinetic energy decreases. Or you can also say speed slash kinetic energy decreases. Or also, what else can you say here? You can say their amplitude of displacement decreases. Displacement, or you can say displacement is a good word. Amplitude of displacement decreases. Let's see this question. Figure 3.1 shows a cylindrical copper kettle that contains cold water. Okay. The kettle is used to heat water. Okay. And there is an electrical heater at the base. Okay. There is an electrical heater at the base. State and explain the advantage of using heating the water from below. Why have we kept the heating element at the bottom? Why? Let's answer that. Very, very easy to answer. What will you say? Since the heating, what has, since the heater, okay, since the heater is at the base, hot, less dense air rises and cooler, denser air, not air, I guess. This is what is the substance inside? Water, sorry. Hot, less dense. Since the heater is at the base, hot, less dense water rises and cooler, denser water sinks to the ground. Water sinks to the ground, developing, or we shouldn't say ground as well, we can say bottom. Sinks to the bottom, developing convection currents. Convection currents. And as convection currents develop, what will happen? This allows for a uniform spread of heat. This allows for a uniform spread of heat. Okay. As the water is heated, it expands. Explain in terms of molecules why water expands when it is heated. Very, very easy. Why does the water expand when heated? The heat provided is used to break what? Intermolecular forces of attraction. Intermolecular forces of attraction. Okay. And as the intermolecular forces of attraction break, what will happen? The molecules will move away from each other as the bonds or intermolecular forces are broken. The molecules move further away from each other. The molecules move further away from each other. From each other. Simple. Let's move on to part 2. Copper also expands when heated. State what happens to the level X of water in the kettle. Explain your answer in the terms of the expansion of copper and water. Okay. So when you heat this thing, obviously the level will go up. Why? Because liquid expands more than the copper. So you can say X rises as liquid, that is water, expands more than solids, expands more than solids. And what is the solid here? Copper. Simple as that, nothing complicated. Okay, let's see this. Copper is sometimes chosen as a material to make pans for heating liquids. Okay. A copper pan contains water at room temperature. Okay. The top surface of the water in the pan cools as water evaporates. A convection current causes the rest of the water to cool. Explain how this convection current is produced. Okay. So, as the water on the surface cools, it contracts, or what can you say? Its volume decreases and density increases. Okay. This causes the less dense, or you can say this causes the more dense water on the surface to sink, to the ground, to sink to the bottom, and less dense less dense hot water rises to the top for cooling. To the top for cooling. So basically, the water on the surface which gets cooled due to evaporation sinks to the ground because it becomes cold and less dense. The hot or less dense water replaces it, and once the hot and less dense water replaces it, at the top, the hot and less dense water also get cooled down by evaporation, rises to the top for cooling. Simple. Let's move on to part B. The copper pan is now placed on a hot plate that is switched on. State the name of process by which thermal energy passes through the base of the pan. The base of the pan is made of metal. Conduction is your answer. Copper remains a solid when heated up to 1000 degrees centigrade. Suggest one other reason why it is sensible to use a pan made out of copper. Because copper is a good conductor of heat. Copper is a good conductor of heat. Simple as that. Let's move on to part C. The water in the pan is heated from 17 degrees centigrade until it starts to boil at 100 degrees centigrade. The specific heat capacity is this, and the pan contains 750 grams of water. Okay, can you calculate the energy? Very, very easy. Q is equals to mc delta T. What will your mass be equal to? 0.75. What is your specific heat capacity equal to? 4200. What is your change in temperature? 100 minus 17. This comes out to be what? 0.75 into 4200 into 83. This comes out to be what? Oh, let's see. This comes out to be what? 2.61 into 10 is the power of 5 joules. This is your answer. Let's move on to the next question. Yeah, this one is an interesting one. This one is, I guess, the most difficult question for specific heat capacity. Figure 10.1 is a diagram for soldering iron. Okay, this is the diagram for a soldering iron. Solder is a mixture of metal used to make a permanent contact between electrical wires. Okay, the heating element, this thing. Let me highlight it. The heating element, this one, raises the temperature of the metal tip. Okay, when solder is placed against the metal tip, the solder melts over the wires to be joined. When solder cools, it solidifies and the permanent connection is made. Okay. The working temperature of the metal tip is what? 380 degrees centigrade. Okay. The boxes in figure 10.2 shows two materials and some different melting points. Okay. On figure 10.2, draw a line from the metal of the metal tip and a line from the solder to a suitable melting point for each. Okay. So can you see the working temperature of metal tip is 380 degrees centigrade? That means its melting point must be greater than that. Any temperature that is greater than 380 degrees centigrade, yes, 1000 degrees centigrade. And what should be your melting point for the solder? Your solder should melt at a point less than 380 degrees centigrade. So any answers like that? 200. Yeah, let's further move ahead. The heating element is rated at 24 volts, 3.3 ampere. The heating element is switched on. The temperature of the metal tip rises from 20 degrees centigrade to 320 degrees centigrade. This is your initial temperature, final temperature in the first 10 seconds. Calculate the electrical energy supplied to the heating element in the first 10 seconds. Okay. So energy is equal to what? Power into time. How will you calculate power? IV into time. What is your current? 3.3. What is your voltage? 24. What is your time? 10. Can you calculate the answer? 3.3 into 24 into 10. This comes out to be 792 joules. 792 joules. Let's move on to part 2. The metal tip is made of copper and has a mass of this. The specific heat capacity of copper is this. Calculate the thermal energy gained by the metal tip in the first 10 seconds. Okay. So Q is equals to mc delta T. Your mass is 2.3 grams, and I wouldn't convert it into kilograms because my specific heat capacity is also in grams, 0.39. What is the change in temperature? The metal tip, sorry. The metal tip goes from 320 degrees centigrade to 20 degrees centigrade. So the change in temperature is 300. Let's calculate the energy. 2.3 into 0.39 into 300. This gives you an answer of 269.1. This gives you an answer of 269.1 joules. Simple. Also, if you convert it till three significant figures, 269 joules. Describe in terms of free electrons the process by which heat transfer through the metal tip. Already done. Already done. You can scroll back the video. How thermal energy is transferred in metal. Heat is lost from the metal tip by convection in air. Explain how convection occurs in air. Okay, very good. Air surrounding the metal tip. The metal tip gets hot. Metal tip gets hot and expands. This causes the air to become less dense, and it rises. Cooler, denser air from the surrounding takes its place. From the surrounding takes its place. Takes its place. Takes its place. Simple. Let's move on to the next part. The temperature. Okay, so this is excluded from the syllabus. Not going to do that. This also excluded from the syllabus. Let's move on to the next question. Okay, let's see this. Figure 4.1 shows apparatus used to measure the specific heat capacity of a metal. Okay. The electrical heater is switched on. Okay, this heater is switched on and supplies 17,000 joules of thermal energy to the block of metal. The temperature of the metal rises from 16 degrees centigrade to 38 degrees centigrade. This is your temperature initial. This is your temperature final. The mass of the block of metal is 850 grams. This is your M. Okay. No energy is lost from the metal. Okay. Calculate the specific heat capacity of the metal. Very, very easy. Q is equals to mc delta T. Okay. What is your Q? 17,000. Okay. What is your mass? 850 grams. 850 grams. What is your specific heat capacity? I don't know. What is your change in temperature? 38 minus 16. Okay. What does your C comes out to be? What does your C comes out to be? 17,000 divided by 850 into 38 minus 16. This comes out to be what? This comes out to be 0.909. 0.909 joules per gram. Degree centigrade is your specific heat capacity. You have to calculate heat capacity of a metal block, although this is excluded from syllabus, but it is very, very easy to calculate. If you have to calculate heat capacity, capital C, you just take the mass and multiply it with the specific heat capacity. The mass was 850 multiply it by 0.909, your heat capacity comes out to be 850 multiplied by this. Yeah, your heat capacity comes out to be 772 uh, 0.7, that is equals to 773 joules. Although this is excluded from the syllabus, but it is just a general knowledge that you can have. Explain how thermal energy is conducted through the metal. Already done that. Electrons hit the molecules. Molecules start energy. Electrons basically move across the metal. When they move across the metal, they hit the molecules. As they hit the molecules, they transfer thermal energy. We have already done this in detail in the previous questions. I guess you can scroll back the video. Okay, let's see this question. Figure 5.1 shows the particles moving in a sample of liquid water. Okay. Explain using ideas about molecules while liquid expand more than solids for the same temperature rise. Okay, why will liquid expands more than solid for the same temperature rise? What can you say here? As heat is added or supplied is a better word, I guess. Supplied, the molecules start to move faster. The molecules start moving faster. And as they start moving faster, what will happen? As the molecules move faster, or you can say, as the molecules move faster or with greater kinetic energy. Basically, you have to compare a solid and a liquid, right? So, as heat is supplied, added, the molecules start moving faster or with a greater kinetic energy. Okay. Since liquid have lower intermolecular forces or weak intermolecular forces have what should we say, lower intermolecular forces, intermolecular forces, the liquid can expand more, the liquid can more expand more. Okay, let's move on to part B. The boiling point of water is 100 degrees centigrade. State the boiling point of water in Kelvin scale. So 100 plus 273, that is equals to 373 Kelvin. Simple as that. The temperature remains constant as water turns from liquid to gas at the boiling point. Explain in terms of particle why energy must be provided even though the temperature stays constant. Energy is needed to break the intermolecular forces of attraction. To break the intermolecular forces of attraction. Intermolecular forces of attraction. Simple as that. Nothing complicated here. Let's further move ahead. Okay, so again we have an electrical heater. Now this will be interesting. An electrical heater is used to heat a sample of metal. Okay. In figure 5.2, there is no thermal energy transferred from the metal to the surrounding during the heating. Okay. The metal has a mass of this, is initially at a temperature of this. The heater is switched on for 2 minutes and then switched off. The maximum temperature rise given by the metal is 40 degrees centigrade. Okay, maximum temperature reached. So this is your final temperature, this is your initial temperature, this is your time, this is your mass. Okay. The power of the heater is this. You have to calculate the specific heat capacity of the metal. First of all, can you calculate energy Q using power and time? Yes, power is equals to 20 multiplied by the time 2 into 60. This comes out to be what? 20 into 2 into 60. This comes out to be 2400 joules. Okay. And what will you say here? Q is equals to mc delta T. 2400 is equals to your mass, that is 200 grams. See, here you have to give the answer in grams. So I will put the mass in gram. C into what is the change in temperature? 40 minus 15, that is 25. So this is your answer divided by 200 into 25. This comes out to be 0.48. 0.48 joules per gram degree centigrade is your specific heat capacity. Simple. Okay, let's see this question. In many countries, solid salt is produced by trapping seawater in large shallow ponds and letting the water evaporate. Figure 4.1 shows salt being produced in this way. Okay, state two ways in which boiling differs from evaporation. First of all, boiling occurs at a single temperature known as boiling point, at a single temperature known as boiling point, whereas evaporation occurs at all temperature, whereas evaporation occurs at all temperatures. Okay, what will be point number two? Evaporation occurs at the surface only, whereas boiling occurs throughout the liquid, whereas boiling occurs throughout the liquid, throughout the liquid. Okay, describe in terms of water molecule what is happening as the water evaporates. Okay, greater kinetic energy molecules escape from the surface, escape from the surface. This decreases the average kinetic energy of the molecules. This decreases the average kinetic energy of molecules. Simple. Hence, temperature decreases. Hence, temperature decreases. Simple as that, nothing complicated. State why the ponds used in this process have a larger surface area. Surface area increases, rate of evaporation increases. Very basic thing. Rate of evaporation increases. Okay. State why this method of salt production does not work well in a country with a cold climate. Why does not it work well in a country with cold climate? A country with cold climate, with cold climate has a lower temperature, has a lower temperature, hence lower rate of evaporation, hence lower rate of evaporation. Let me scroll down a bit. Lower rate of evaporation. So this marks the end of theory past papers for specific heat capacity. If you have any questions, you may ask.